start ಮಾಡಲಿ.
हाँ मा
In today's, I will welcome all of my teammates to this online review video. I will deal with the forward bias, all the things about that, the circuit diagram, the working, and the definitions and basic concepts of that. So, in a semiconductor diode, forward bias refers to the condition in which the positive terminal of the external power supply is connected to the P-type region and the negative terminal is connected to the N-type region. This reduces the width of the depletion region at the junction, allowing charge carriers to move freely across the barrier. Because the potential barrier becomes smaller, electrons from N side and holes from P side gain sufficient energy to cross the junction. As a result, significant current begins to flow through the diode. Once the applied voltage, which is typically around 0.7 volt for the silicon diode, which we are using in current situation or in the diode, amount of resistance. Now I will share my screen and so we can see in this multi-sim simulator, the below diagram is the circuit. So explaining about the circuit, the forward bias circuit, this is the forward bias circuit, a simple forward bias circuit like this. One that's alternate power supply and a diode one diode and similarly current and prevents the diode from damage due to excessive current flow. When the diode voltage is greater than the diode's threshold voltage, the depletion region and current begins to flow. Typical representation of forward bias is shown using a VI characteristic curve. This is the VI characteristic curve. Uh, if I pause this one, we can see that curve. So when at first, as the forward voltage increases, almost no current flows because the diode is still overcoming the barrier potential. Once the applied voltage reaches the knee voltage or the breakdown voltage or the threshold voltage, the current rises rapidly with only a small amount of increase. It indicates that diode is now in its conducting region or conduction part. The diode clearly shows how a diode offers high resistance before the threshold and very low resistance after conduction begins. This behavior is what makes diodes useful in directing current flow and protecting circuits. So this is all about forward bias. Now Chandan will continue the reverse.
Now, as coming to reverse bias, a PN junction diode is constructed by joining a P-type semiconductor and an N-type semiconductor together to form a single crystal. The P-type region is doped in acceptor impurities, creating an excess of holes, while the N-type region is doped with donor impurities, producing high concentration of electrons. At the boundary where these two regions meet, electrons and holes diffuse across the recombines, forming a depletion region that contains free electrons and charges. Then, as coming to the working of this circuit, in this circuit, the PN junction diode is connected in the series with the AC voltage source and the resistor to demonstrate its basic working principle. When the AC source applies a positive half cycle, the diode becomes forward biased, allowing the current to flow through the resistor. During this condition, the diode conducts only after crossing this threshold voltage, typically around the 0.7 volt for silicon diodes. As a result, the output voltage across the resistor appears during the only positive half cycle in the waveform. In this negative half cycle, the polarity reverses, making the diode reverse biased. And now, as coming to the graph, how it runs is, then as coming to this graph, the above graph represents the output voltage waveform in the PN junction diode of circuit when subjected to the AC input. In the first graph, the waveform shows that the diode is blocking the positive half cycles and allowing only the negative half cycles to pass. This indicates that the diode is oriented in reverse bias with with respect to the input AC signal. As a result, the output displays deep negative voltage dips while the positive portions remain applied near zero. In And this completes the reverse bias. Next, I will tell Janvi and Kirtana to next part of that is half wave rectifier.
Now I'm going to explain the half-wave rectifier. A half-wave rectifier is an electronic circuit that converts alternating current into a direct current by allowing only one half cycle of the AC waveform to pass through while blocking the other. It uses only one diode to allow current to flow during a one half cycle of the AC signal. As a result, the output is pulsating DC that contains gaps because only the positive half of the AC waveform is used. Half-wave rectifiers are mainly used in a low-power application, basic power supplies, and teaching purpose due to their simple construction. Although easy to build, they are less efficient compared to the full-wave rectifier. So coming to the working, I'm going to share the screen. This circuit is a simple half-wave rectifier that converts AC voltage into pulsating DC. The AC source provides 100 volt 50 Hz to the primary side of the transformer, which then delivers a suitable AC voltage at its secondary winding. This AC from the secondary goes to the diode D1, which works like a one-way gate. During the positive half cycle of the AC wave, the diode becomes a forward bias and allows a current to pass through it. The current then flows through the load resistor R1, 1 kilo, producing an output voltage across it. During the negative half cycle, the diode becomes a reverse bias and blocks the current, so no current flows through the resistor. As a result, the output is not continuous, but a pulsating DC. It means only the positive half cycle, the AC signal appears at the output. The ground connection completes the circuit part. Now Kirtana will continue.
Now I am going to share the screen of the graph of the half-wave rectifier. Okay, this graph shows the output current waveform of a half-wave rectifier. The x-axis represents the time in seconds, while the y-axis represents the current in amperes. The distinctive pattern of pulses with gaps in between is a typical for a half-wave rectifier. Half-wave rectifier output. The graph displays the periodic pulses of a current, each corresponding to the positive off cycle of the AC input signal. During the each cycle, the current rises sharply, reaches a peak and then drops back to zero, creating series of isolated peaks. Between the pulses, the current remains at zero, indicates that the rectifier only allows the current flow during positive portion of the input waveform. And then overall conclusion of this assignment is in a semiconductor electronics Forward and reverse biasing basically decides whether a diode behaves like a doorway. Under a forward bias, the diode conducts because the potential barrier becomes small enough for a charge carriers to move freely. Reverse bias does the opposite. The potential barrier increases, charge carriers are pulled away from the junction, and the diode blocks current except for a tiny leakage. Off wave rectification puts these two modes into practical action. When an AC input is applied, the diode only conducts during the positive off cycle, acting in a forward bias. During the negative off cycle, the diode instantly switches to reverse bias and blocks the current, preventing negative portion of the waveform from passing through. Overall, these concepts highlights a fundamental idea. By simply controlling the direction of charge flow using the diode's two biasing states, we can shape and manipulate the AC signals into a usable DC. Understanding these basic behaviors is the foundation for a more advanced rectifier circuits, power electronics, to operate. Okay, thank you.
Thank you, guys.